Hi friends, today we are going to see how to design a double stub matching network. Before understanding what do you mean by double stub matching network, let us understand why we need double stub matching network. So, double stub matching network is advantageous over single stub matching network in basically two ways. Here the diagram shows a single stub matching network in which the load is being matched with the source impedance by using two design parameters. One is the D, which is the distance from the load, and L, which is the length of the stub. If suppose the load is variable or if it changes, then the D and the L, that is both the distance and the length of the stub, changes. This is because both of them depends on the load impedance. Therefore, we have two design parameters which are changing with respect to the load. Now here comes the advantage of the double stub. Whenever we are using double stub matching network, then the distance between the stubs and from the load is constant. And of course the length is changing. Therefore, now the design parameter D is independent of the change in the load. Hence, we say that double stub matching network can be used for variable loads. Also, as we know that the D and L in the single stub matching network, it is really difficult to manage to get the exact location on the transmission line to place the stub. Hence, even double stub matching network where D is stable, we can find an appropriate position and the tuning will be better. These are the basic two advantages why we use double stub matching network. Now let us consider a load which is given as RL plus minus XL, which is to be connected to a source whose impedance is, let's say, Z0 via a transmission line. Now, how the double stub structure will look like? Of course, as the name indicates, it will have two stubs. So this is first stub, this is second stub. The distance of the first stub and the length of the first stub is given as D1, L1, whereas the distance of stub 2 and the length is given as D2, L2. We will analyze the signal at two basic points, which are shown with the dark spots over here. Because we are dealing with shunt stubs, instead of working with impedances, we will be work on admittances. Therefore, we will evaluate what are the admittance at the interface of first stub, which is called as Y11, and at interface of stub 2, which is called as Y22. We see over here that Y11 is nothing but it comprises of two elements. One which is coming from the transmission line side and the second one which is coming from the stub side. As both are parallel, we can have, let's say, two elements. So we name them as YD1, which is coming from transmission line side, and we have YS1, which is coming from stub side. Similarly, Y22 can also be decomposed into two subpoints, that is YD2 and YS2. With the circuit theory analysis, we can say that because YD1 and YS1 are parallel to each other, therefore they will be adding. So we can write as Y11 to be equal to YD1 plus and minus YS1 and Y22 to be equal to YD2 plus and minus YS2. We note that now instead of Z0 we have admittance of Y0. Correct? So now we have to match to Y0. To understand the technique more thoroughly, let us consider a problem. The problem states that we have a load impedance of 100 plus J100 ohm, which is to be matched to a characteristic impedance of 50 ohms. The first stub is placed at 0.40 lambda away from the load, and the spacing between two stubs is given as 3 by 8 lambda. From the problem, you can analyze that three major things are given. First is the load impedance. Second, the distance of the first stub from the load. Third, the distance between the two stubs. We can draw the circuit like this. We have D1, that is the first distance 0.40 lambda, and the second distance D2, which is 3 by 8 lambda. Okay, and we need to calculate YD1, YS1, L1, L2, YS2, YD2, and Y22. Let us go ahead and solve the problem. First step is to normalize and plot the normalized impedance on a Smith chart. The process for normalization is, we have ZL, which is 100 plus J100 ohm. Characteristic impedance given is 50 ohm. So we divide the characteristic impedance to we divide the normal impedance to the characteristic impedance to achieve the normalized impedance, and we get 2 plus J2 ohm, which has been plotted as shown in the figure. How to plot this? We have to find the resistance circle, which is this circle, as with a value of 2, and we also wanted to find the reactance circle of having a value of 2, and wherever they intersect or meet, that point is the ZL impedance as shown in the figure. Next step is to get the normalized admittance, because we will be working in shunt stubs. So instead of working in impedances, I'm working in admittance. So let us find the admittance. How to find the admittance? Let us see using Smith chart. So first step is to plot a VSWR circle, which is shown here with the dotted lines. You can see here. How to plot this? Take this much of radius in your rounder. From center to point ZL, take the radius. Draw a circle. Then you stretch a line which passes from the center of the Smith chart, ZL, and which cuts the circle on the other side. Wherever it cuts the circle on the opposite side, we call it as diametrically opposite side. That is the point of YL. Read the value of YL. See what value of circle, real value circle and the reactant value circle passes through this point. That is the value of YL. From the Smith chart, the value comes as 0.25 minus J0.25. This you can verify by easily calculating YL on your calculators. You know that ZL is 2 plus J2 ohm. Take the inverse of this and you will find 0.25 minus 0.25. That is the value of YL. Stretch the line outwards and mark the value of wavelength towards the generator scale, which is the last scale. The value comes as 0.458 lambda. Now, a very important concept in double stub matching network is the concept of spacing circle. Let us first understand what do you mean by spacing circle and why we need spacing circle. For that, we will go back to our circuit diagram and do some analysis. Here we can see that we have plotted ZL, which we have converted to YL. We know that from YL, if I move 0.40 on a transmission line, I'm going to reach Y11. After 0.40 lambda, I will walk 3 by 8 lambda. When I move 3 by 8 lambda, I will reach a point where my Y22 lies. And Y22 should be such that after which I have achieved the center of the Smith chart, or I have reached the center of the Smith chart, which means I have already been in a matched condition. That means Y22 should be on a unit circle, isn't it? Because once I have done with Y22, okay, I have already been matched. That is, I'm at the center of the Smith chart after stub 2. That means the real part of Y22 should be 1. This demands that YD2 real part should also be equal to 1. For YD2 real part to be 1, Y11 real part should also be equal to 1. That means Y11 should be on a unit circle. But how y11 can be on a unit circle? If yd2 is on the unit circle, then the distance between y11 and yd2 should be 3 by 8 lambda. That means there should be another unit circle which is at 3 by 8 lambda distance away from y22 point, or the original unit circle point. So we will introduce one more unit circle which we called as a spacing circle, which is 3 by 8 lambda away from our normal unit circle on the Smith chart. How to draw the spacing circle? So the real part of y22 must be 1, so yd2 must be 1. Instead of I'm saying yd2 to be 1, I would suggest that to be the real part of yd2 must be 1. That is, it must lie on the unit conductance circle. Now how to draw the spacing circle, let us see. So the first step in the spacing circle is to calculate 3 by 8 on the Smith chart. Now here we will use wavelength towards the load, because what I'm doing is I'm coming from the matched point towards y11. What is the match point? The match point is the point at which my source is being mentioned, or my source is kept. Okay, so y0 is a point where the source has been placed. So I'm coming from source and moving towards the load. Hence, to calculate this 3 lambda by 8 or 3 by 8 lambda on the Smith chart, we will use wavelength towards the generator. Sorry, wavelength towards the load, not the generator. Now, how to find this wavelength towards the generator is very simple. We know that here one complete revolution of one complete rotation on a Smith chart gives you 0.5 lambda. That is 0.25 and half the way 0.25. So it is total 0.5 lambda. 0.5 lambda equals to, it is 360 degrees, right? So how much will be 3 lambda by 8? So that is a very simple mathematical calculation. It will come to be 270 degrees. So 270 degrees, if I consider this will be 0 degree, then above will be, here will be, this side will be 90 degrees, then this side will be 180 degrees, and then here it will be 270 degrees. So I will mark a line which passes from the center and an angle of 90 over here, which is marked as minus 90. You plot a straight line down. Find this dotted line's bisector. So stretch, it is written over here, stretch a line from the center of the Smith chart. This is the line that we have to stretch, which is shown in dotted. Then find the bisector of this dotted line, okay, which is shown in blue. Then draw a spacing circle. After drawing the bisector, draw a spacing circle. So this blue curve shows the spacing circle. Once you have jotted the spacing circle, then the next part that we will do is we will find what is the value of yd1. We know that as from this figure you can see, we have a load, and from the load, if I move 0.40 lambda, then I will reach yd1 value. So to reach the yd1 value, I need to move 0.40 lambda on a transmission line. Moving on a transmission line is equivalent to moving on a VSWR circle. So this was my load, that is my YL, which is located at 0.458 lambda. If I moved exactly 180 degrees, that is diametrically opposite, I have moved how much? Half the circle. Half the circle means 0.25 lambda. So I will add 0.25 in this value. Okay, that means I have moved. So when I move from here diametrically opposite, it is 0.25. I will calculate what is the value over here. You just check it out. What is the value of value that shows over here when you moved exactly 0.25 lambda, that is diametrically opposite. And when I've come to this point, it is already 0.25 distance has already been traversed. Now you have to travel more to achieve 0.40, isn't it? 0.25 is achieved when you have reached here. At this point is 0.25 has been already finished. Now the rest you will walk and you will come to a point over here. Okay, so that will give me the value of 0.358 lambda. So the distance from 0.458 lambda to 0.358 lambda is 0.4 lambda. Okay, so